The second effect or the second implication of the special relativity now deals with, because I already said that we are going to look at the fundamental nature of space and time, right? So one we looked at from the point of view of simultaneity. Now another implication is on the measurement of time, right? So that means the way we perceive time in different frames, right? And in general, loosely speaking, what we are meaning by perceiving time is that how do we measure time, right? Or what is our standard of measuring time? So normally we say that, okay, fine, so time we are counting in terms of seconds, or milliseconds, or microseconds, or whatever, minutes and hours and all that. But these are all calibrations, right? We do define what do we mean by 1 second, right? And then, for example, in mechanical clock, 1 second could be equal to 1 cycle of a simple pendulum. When a simple pendulum starting from its extreme location goes back to the other extreme, comes back, that is calibrated to, or that is considered equivalent to 1 second for a particular pendulum, right? So that's a standard. And then you say, every time this thing happens, I'll count 1 tick, which is corresponding to 1 second, right? Now what we are saying is, this itself now, this whole process loses meaning in an absolute sense unless you also define in which frame you are measuring this, you are making this measurement, right? And again, by frame, I am not saying that on the particular characteristic of the frame, but only the inertial nature. That if the frame is stationary with respect to a particular inertial frame, or my frame is actually having a relative motion, and then what is the magnitude of that relative motion, right? So, and the effect is normally termed as time dilation. So it's about the measurement of time, right? And for this, to explain this again, let us try to devise thought experiment. So let us say, just like I said in the previous case, let me say this is also a, let's say, train car, right? It's just a bogie, right? So it has some wheels. It is free to move in this direction with speed v. So later on we'll use that. The way I'm going to measure time in this, so let me call it this as again my S prime frame. And the way I'm going to measure time here is, I'll put a light source here, right, which emit lights. I'll put a mirror at the top, right. So light basically goes at the top, gets reflected, come back down, and here I have some kind of a detector, right. I don't have to worry about the actual setup, right. This is a thought experiment, right. However, could be realized, right. So I'll also put a detector, and then the detector gives me a click sound. So let's say it's connected to a speaker or whatever. Click sound. So this one emits the photon, and we say 1 second or the unit of time is when the photon has gone to the top, gets reflected, and came back. Right. So the round trip of a photon is defined as unit of time. So in S prime, round trip of photon is unit of time, right? And what is that? Let me write it as T prime, right? And T prime in this case is then, I know what is the speed of photon, I know photon moves with the speed of light, so it's C. If I know this distance, let's call it H. If I know this distance, then I can find out this time, right? I mean, there is nothing new that can come here. Right? So T prime is equal to 2H by C. This is the time I'll measure. So if this is my clock, and then every other event is happening inside this car, and I'm measuring the time for those events using this clock, then this is the unit of time. Time passes at this rate. Every tick is corresponding to T prime. Right? Do not worry about the actual realization of this, but rest assured that if we want to realize this, it can be done, right? And the result that we are going to derive will be commensurate with an actual experiment, if one could actually do it. Okay, so T prime is 2H by C, right? Fine. Now let's go to a different frame. So now let me go to again X and T, right? A frame S relative to which S prime is moving with speed V, right? And now let us see the same event of single tick T prime from the point of view of observer stationary in S. So let's say I am standing here and I look at this car moving and the same event happening. And for me also, I'll say that let's start counting the ticks, or we'll try to see that how much time is elapsed. So as soon as the photon leaves here, I start waiting. The photon goes there, the photon comes back here, and I say, okay, fine, now that's a 1 second, right? So let us see how long I measure that 1 second to be, right? Now for me, or for the observer who is stationary with respect to who is a stationary observer with respect to whom the car is actually moving, for me, what I measure is, let us say, when I start observing for the first tick, the light source is here, right? As soon as the photon leaves, since this card is moving, right? Of course, the location of the mirror is going to change. So initially the location of the mirror was this. When the photon left this side, right? When the photon actually reaches this height, the mirror could be somewhere here. Right? So it must have traveled a distance v and some time t. Right? The mirror actually traveled there. So the photon actually has to travel this much distance. Right? And now again, don't worry about the slanting of the photon and all that. One can explain that. If it involves it too much, just think about it slightly and you will explain this. However, anyway, so the photon actually now travels this distance rather than the vertical distance, and then it reflects back, right? And then comes back towards the source. So the source is at this point, the source is also here, right? They are both moving together, right? So the source and the card itself moves together. So the card was like this here. Then by the time the photon reaches the top, this top, the card has moved here. So effectively for me, the photon has gone something like this. And then by the time the photon comes back, the card has moved another Vt, right? So it has basically come down somewhere here. And here, once it comes here, I start listening, I hear the single click, right? So for me, the events are slightly different. The way the measurement is happening is slightly different. However, right now I am not interested in all this optics. I am more interested in what is the time that I measure, right? Okay, so now for me, again, the time is, I know that, okay, so in S, we know speed of photon is c, right? We already established that this is not going to change. So, time is distance traveled divided by c, just like here. However, what is the distance traveled? In my frame, the distance traveled is more because the entire frame is moving, the mirror is actually continuously moving, right? So in my frame, I have to find out what is the distance traveled. The distance traveled is in half round trip, it's h, this height, and vt, right? So if the full round trip is t, then now I know from symmetry that it will take half the time to go up to the top, it will take half the time to come to the bottom, right? So vt by t. So then this t is basically this distance twice, so 2 h square plus v square t square by 4 divided by c. Right? And if this is the case, then again now I can solve for t, and what I'll get is t is equal to twice h by c square root 1 minus v square by c square. You can solve this. This is the time that I get. Twice h by c is nothing but the time it took for this round trip in S prime frame. So this implies t in S frame is t prime into 1 over square root of 1 minus v square by c square. The interval for same event, this is the interval, this is the time interval. This is my definition of time. The interval for same event, exact same event happening in two different frames is rather different, and this term is written as gamma. This is the relativistic correction factor, or this is the relativistic factor, right? Gamma. So I can write this in terms of gamma as gamma t prime. and this is the time dilation. Because once you put in values here, see, V is always going to be less than C, because C for time being is the ultimate velocity that one can reach. So if V is always less than C, then the gamma is always greater than or equal to 1. And if that is the case, then for the same event, the time duration that you measure for the event which is happening in a frame which is moving with velocity v with respect to the stationary observer, right? We are always going to measure a larger time interval, and that means time in moving frame runs slower. So this is termed as time in moving frame runs slower, or it is also written as clocks in moving frames run slower, right? So the percentage of time is different depending on which frame you are considering, and this is termed as time dilation. So for example, something which happens in 1 second in S prime frame, right? Because gamma is greater than 1, will happen in 1.2 seconds or 1.5 seconds or 1 point something seconds, right? More than 1 second when looked from this frame S. So for this frame S, it will seem that the same event takes much longer time. That means the clock is running slower. Okay. So this is the time dilation. Now I am not going to go into the analysis of the next aspect or the next implication of displacement of relativity. Right? I am just going to state that here, and then we'll go on to maybe a few examples. And the third important one is then length contraction. And what this states is, just like time in a moving frame is different from time in a stationary frame, and in fact moving frame the clocks will run slower, they are connected by a factor gamma. Length in moving frames are different from lengths when observed from stationary frames, and they are connected by the same factor gamma, but L prime over gamma. Right? So this is your frame S, this is your frame S prime. So for example, well, not in this case, but in the previous example that we took, and that's the reason why I said that let me take the length of the car when observed from frame S to be L rather than L prime originally, right? The reason for that was because this length will be not different. So let us say if this is an object, right, and a person is sitting in this object and asked to measure its length with whatever way. Let's say it measures its length as L or L prime rather, right? And if this object is moving with respect to a stationary observer, and he is also asked to measure the length of this object, right? While being stationary and the object moving away from it or towards it with velocity v to measure this length, he will measure a length L, right? And L is not equal to L prime. Right? And the effect is because of the special theory of relativity, that is because of the constancy of speed of light. And what this means is, and more accurately, the length measured here will be L prime by gamma, and since gamma is greater than 1, we will measure lengths to be shorter. Right? So length of moving objects become contracted, time durations in moving frames become elongated, so time dilates whereas length contracts. So this is termed as length contraction. Right? So these are the three important implications or three important results coming from the special theory of relativity. It's very important to understand this, and at the moment, even if you can find a lot of contradictions there, a good way of a good pivot point to get rid of all the contradictions is not to see these effects as spatial effects coming because of a particular example being considered or the particular way we are describing the examples using geometry. The pivot point is that these are extremely fundamental real effects which actually affects our notion of space and time rather than anything else. Right? So it's not that my observation somehow changes things, the things actually change. Right? And we'll discuss maybe examples, but for example, one way of looking at it is, or one way of kind of explaining these different scenarios is that the space and time as perceived in one frame, x prime t prime, xt, these are not equivalent as perceived from another frame, right? So saying that, so it's not as if an observer, a moving observer and a stationary observer are moving in this, are measuring in the same xt landscape. The landscape itself are different for these two observers. So of course their results are very, very different. They are fundamentally different. Right? Anyway, we'll discuss that more further. For a time I'll stop here and we'll start from here in the next one.